Hi, I'm Ron Caplan from Predictive Science Inc. We hired an intern to explore do concurrent for us, gave him lots of work to do, and it culminated in a paper for WACCPD. And so this is sort of a summary of his talk and of our paper. So basically, we're asking, can Fortran do concurrent replace directives for accelerated computing, going right off of the last slide from the previous talk. So you all know about directives, how great they are. You know, they're easier to write than low-level APIs. The performance can be similar to low-level APIs sometimes. They do have some degree of portability, and they have minimal code interference so that domain scientists don't get freaked out by a bunch of complicated CUDA code, for example. But the cons are they're not always supported on every platform, like we just saw. Also, their specification scheme is more fluid than the language spec oftentimes. So sometimes it requires you to rewrite how you do your directives once a new version comes out or they make something better. Also can make the code harder to read. So for example, if you're doing a deep copy of a large structure in OpenACC, you know, you can have like a gigantic paragraph of directives for every, data copy there. Also for like OpenMP offload, you can have a huge paragraph of directives for all the different device types for different optimizations on every loop. So ideally, standard languages have started to go away from, C++17 standard parallel algorithms and Fortran do concurrent are ways that, in theory, you could go away from directives. And so our goal here was to just test what's the current status of doing that using, the compilers today. We only chose 3 compilers to use, but so to do that, we have a test code called Diffused, which is it's a tool that we use to smooth out magnetic field data from the surface of the sun in order to use it for our MHD models of space weather. And we used a 8 million point real world problem to test this on. This code basically is a stencil code, finite difference, explicit code, and it's makes up of a bunch of vector operations, array operations, stencil operations, and there are reductions for the polar boundary conditions. What this code does not have is there's no MPI, there's no atomics, no multi-GPU, no derived types, no function calls within the loops. So this is kind of like a cheating case in a way, in the sense that all these things on the right might completely break all of this, but we'll talk about that later. So we used basically GFortran, NVFortran, and iFort, the newest versions that we had at the time. And we ran this on basically a dual socket epic on Bridges 2 and an A100 40 gig on a DGX at San Diego State. And we ran all our codes through a Singularity container in order to be able to just plop that on different systems and run it. And we also provided a reproducibility package that you can right now go and download and run this and test it yourself. Basically for baseline performance, all the compilers perform similar to each other for the CPU, both the serial code and the multi-threaded code. I should mention that what we call the original code here is using OpenMP for multi-threaded CPU, and it's using OpenACC for GPU. So there's no target offload or anything. And it also can use OpenACC for multi-threaded CPU as well. So on the GPU side of things, we see that the NVIDIA compiler is faster than GFortran for OpenACC, but that's kind of common right now. I'm sure that'll improve later as we go along. So just a overview of do concurrent. Everyone here probably knows what that is, but here's an example. On the top code, you see this is just one of the loops of the code, and we have our OpenMP on there, we have our OpenACC on there, and there's nested do loop. So all of that code can just be condensed down to the 3 lines at the bottom. And that's kind of the ideal situation that we would like. But do concurrent, all it really means, according to the spec, is that the loop can be executed out of order. That doesn't mean that it's parallelizable, right? So a key thing, for example, is atomics and reductions. So anything that you're doing, if you do a reduction in a do concurrent loop, that's not according to spec necessarily, right? So if you parallelize it, if you don't parallelize it, it's fine, right? You can do any order, but it's still an issue. So they are adding reduction to do concurrent in Fortran 2020X when it comes out, but there's still going to be things like atomics device selection, conditionals, all those things in OpenACC and OpenMP we like that are definitely not part of the language now. So, you know, there's going to be some limitations here, but so what we did is we made basically 4 versions of the code. So we have our original code, which is using the directives, like I said before. We have a serial code just for a check where we don't have any directives at all, just do loops. What we call here the new code is where we have sort of a spec compliant version. So any loop that can have a do concurrent on it, like no reductions, we have do concurrent and no directives. But then we keep the directives for data movement for OpenACC for the GPU, and we also keep it for reductions. And then on the far right, we have our experimental code, and that's basically where we take out all our directives and see what happens, right? So that's sort of what we would say is the ideal situation where you have no directives at all. These are just the compile flags to do all this. I won't go through this in detail. Just to note that on Fortran, they don't support do concurrent multi-threading directly. So in order to actually parallelize those loops, we have to use their ftree parallelized loops flag, which is an auto parallelization feature in Fortran. And you have to set the number of threads at compile time. That's the only way to sort of parallelize those, but it does work, as we'll see. So here's our NV Fortran results. On the left, we have the GPU results, and we see that whether we use the original code, which is the OpenACC, the sort of spec compliant code, which is a mixture of the two, or even our experimental code where we don't have any directives at all, we get roughly the same performance. So for that experimental code, what's happening there is that the NVIDIA compiler is using unified managed memory. And then it's also implicitly detecting those reductions and implementing them correctly, even though the spec doesn't say to do that. On the right-hand side, we see that for the CPU multi-threading, once again, the performance is roughly the same all the way across. So for the NV compiler, everything's fine. We can completely get rid of our directives and everything is, you know, perfectly good. Switching to Fortran, so on the GPU side, there's no support for do concurrent GPU offloading yet, I hope. And so basically by switching to do concurrent, we just destroyed our Fortran GPU capability at this time. But on the CPU side, everything is okay. The performance on the experimental code, where it's using the auto parallelization for everything, is not as high as the other ones, but it's roughly in the ballpark. So we don't lose the CPU. And this is important because even if we're just going to only use NVIDIA for the GPU side of things, we do use Fortran a lot when we run on the CPU. So we want to make sure that we don't lose that multi-threaded parallelism. And here we don't by using the auto parallelization flag. And then for Intel, basically, obviously, they don't have GPU offload support for NVIDIA on anything, so definitely not do concurrent. But on the CPU side, for the compliant code, which is where you have still using OpenMP on the reductions, but using do concurrent everywhere else, the code runs fine and actually runs faster. And they actually support do concurrent directly using the FOpenMP. They say in their documentation that they actually parallelize that do concurrent and recognize it. The experimental code where we have no directives, there the code gave wrong answers, and that's because it's, you know, we had a reduction loop and we put do concurrent on it, and the compiler, instead of recognizing that and implementing it correctly, it didn't do that, but it also didn't say, hey, this is a reduction, you can't do that, I'm not going to compile. Instead, it just parallelized it and had the race conditions included and got the wrong answer. So you might look at that as a compiler bug, or just that we're not coding according to spec in that case. So I'm not sure which way you look at it. So basically what we find is that NV Fortran, you know, do concurrent support for GPUs. We lose our Fortran GPU support if we switch over to that completely, but we may gain Intel GPU support. Intel has said in a presentation that they plan to have do concurrent offloading for Intel GPUs. So by doing this switch, we might actually gain some portability there. For our experimental code, you had to rely on unified memory and instead of our manual data movement for OpenACC. And here, there was no performance loss by doing that. But there could be, depending on more complicated codes. We retained our CPU multi-core parallelism, except for the case with Intel where it got the wrong answer. And then I've already said all this. And then, yeah, the implicit reductions just aren't supported everywhere. So the performance is on par for all of it for this code. So that's great. And so in summary, basically, do concurrent does allow for cleaner code. It increases with future proofiness, if you want to make up a word. This is a recent tweet I found online that says, in 30 years, will Google even exist? Who knows? But will you still be able to compile your Fortran code from 1990? For sure, right? So if you can switch your code to a standard language, it has a lot of robustness for the future compared to anything else. So with ND Fortran, we are able to eliminate all directives, but basically using a combination of the two gives us the best results and the best compatibility. So retaining sort of our manual data management and doing the reductions because they're not supported yet in do concurrent is sort of the best way to go for now. So basically, can you replace them completely? The answer is yes, with the caveat of using NV Fortran, using NVIDIA GPUs, and for some codes, like simple ones like ours. If you want more details on this, here's an archive link here and for the paper, and then the DOI there for Zenodo is the reproducibility package. And our next step is to actually apply this to the POT3D code, which is part of the spec HPC benchmark. And the added complication there is that it's a multi-GPU code with MPI, and it also has atomics, and it also has automatic arrays that aren't allocated, in which case managed memory isn't a thing. So basically, spoiler, it does work. We have to basically use memory management with OpenACC, and we still have to use our host data use device around the MPI calls for CUDA MPI. But in terms of all the other loops and everything, we get away with do concurrent. So we can't get rid of all of the directives, but we can get rid of a lot of them. And so that's kind of the idea is, you know, at this point, like if this continues, I actually view OpenACC not as its own API, but more as a augmentation of the sort of the base languages. Like OpenACC is an accelerator augmentation of the language that keeps getting, hopefully more and more minimized as the languages progress, but they progress so slowly that you have to sort of do this now. There's all sorts of other issues here that come into play, but yeah, so I mean, where this works, it works great. And if Intel follows through with what they're doing and HPE starts supporting it, and if GFortran starts supporting it, then this would be a great way to parallelize code without having to use directives. Or use less directives than normally you would have to. And just to show the reproducibility package that we have, it's pretty simple. There's just this little script. You just fill in these little 4 pieces of information, and then you can just build and run. And it uses the Singularity containers, and if you have Singularity installed, obviously. And it'll just run all the tests from the paper. So you guys can have fun with that. But that's about it.